Hello, everyone. I'm Shigang Li, a postdoc researcher from SPCI Lab, ETH Zurich. Today, I represent Ok-Topk. Ok-Topk is a novel sparse Allreduce algorithm, which is proposed for distributed deep learning training. Ok-Topk has less than 6K communication overhead, which is asymptotically optimal. Ok-Topk is also more scalable than the other algorithms. First, let's look at the evolving trend of modern neural networks. The model size is growing exponentially. Compared with the vanilla transformer model, the model size of a recently released model, Wudao 2.0, has increased for more than 8,000 times. So training for these monsters is both time-consuming and money-consuming. Now let's look at how to speed up the training process on parallel machines. Here we have three major approaches: data parallelism, operator parallelism, and pipeline parallelism. In operator parallelism, each worker maintains a slice of the model, and it requires communication for each operator or each layer to gather the input data. In pipeline parallelism, a consecutive layers from one pipeline stage, it requires point-to-point communication to transfer data between pipeline stages. But today, here we focus on data parallelism. Data parallelism is easy to implement. However, using data parallelism alone may not work for large model training, simply because the model may be too large to fit in device memory. So usually, data parallelism works together with the other approaches to train large models. But data parallelism may also have high communication overhead, the Allreduce communication. So this is also the issue this work, Ok-Topk, aims to solve. Now let's look at where the Allreduce come from for data parallelism. Here is a simple neural network model and an objective function f, in which W denotes the model parameters, and the capital F is the loss function, and C is the data batch sampled from the training data set. So the training process is essentially to update the model parameters to minimize the loss value using the gradient. In data parallelism, each worker maintains a copy of the model, and each worker samples different data batch from the training data set. After the computation of the local gradient is finished, it will conduct an Allreduce operation to globally synchronize the gradients among the workers. Next, let's revisit the traditional dense Allreduce algorithm, Rabin-Sifner's algorithm. Here, suppose we have 4 workers, and they will conduct an Allreduce algorithm to synchronize the dense gradient space. So in Rabin-Sifner's algorithm, it has 2 phases. The first phase is reduce scatter using recursive halving. And after that, it will conduct all-gather using recursive doubling. And eventually, all the workers will get the reduced dense gradient. Here we use the simple latency bandwidth model to analyze the communication cost, in which alpha is the latency, beta is the transfer time per word, and P is the number of workers, and N is the message size. So the communication cost for Rabin-Sifner's algorithm is modeled by this formula. We can see the bandwidth overhead is approximately equal to 2N, which is optimal and also very scalable. But here, N is the number of parameters in the model. Therefore, for large model training, the communication cost for dense Allreduce is very high. To reduce the communication overhead, people propose to use gradient sparsification, namely Topk SGD. In Topk SGD, each worker only selects the largest k out of n values from the gradient space. And usually the density k divided by n is around 1% or even less than 1%. Here in this figure, the crossed block represents the local Topk value and their index. Now the question is how to reduce these sparse gradients. There are several algorithms. The first and also the most simple one is the all-gather-based sparse Allreduce. We use Topk A for priority. So in the first step, all workers will select the local Topk values and their index. And after that, each worker will package the sparse gradient into consecutive buffer. And then it will conduct a standard all-gather operation to gather the sparse gradient. And at last, each worker will do local summation to produce the reduced top K value. Here, the communication cost for top Ka comes from the all-gather phase, and it can be modeled by this formula. We can see the bandwidth overhead is proportional to the number of workers P. So this means that top Ka is not scalable. The second algorithm is dynamic sparse Allreduce. We use top K DSA for brevity here. This algorithm is inspired by Daint's Rebesafiner's algorithm. So in the first step, all the workers will also select the local top K values and their indices. And after that, it will conduct reduce scatter over the sparse gradients. And here, the start block represents the reduced top K values and their index. So we can see the gradient space, the gradient region becomes denser after the reduction phase. This is because the distribution of the local top K values is different among the workers. So we call this problem the filling issue. In this example, we can see for P2 and P3, more than half of the gradient values are non-zero. So this means that there will be no benefit to use the sparse format. Therefore, in top K DSA, it will dynamically switch it back to dense format. And after that, it will conduct all-gather using recursive doubling. And the communication overhead for top K DSA is modeled by this formula. We can see the bandwidth overhead falls in this range. In the best case, in which the top K values has the same distribution among the workers, it incurs 4K bandwidth overhead. But this is hardly achieved in reality. In the worst case, the all-gather phase will completely degrade to dense format, in which it incurs 2K plus N bandwidth overhead. So therefore, we can see the top K DSA algorithm suffer from filling issue when scale up to more number of workers. The third algorithm is called global top K. We use G-Topk for brevity. G-Topk is a tree-based algorithm. First, it will conduct a reduction tree. To get rid of the filling issue, for each level of the conduction tree, it will conduct top K selection operation. So at last, on the root node, here is P3, it will get the global top K values. And then the global top K values will be broadcast from the root node following the broadcast tree. The communication cost for G-Topk is modeled by this formula. You can see the bandwidth overhead is proportional to log P, but this is still suboptimal. Furthermore, G-Topk solves the filling issue, but this is at the cost of high top K selection overhead. Next, let's compare the parallel scalability of the previously discussed dense and sparse Allreduce algorithms. Because we focus on large model training, in which the bandwidth overhead dominates, here we only keep the bandwidth term. On the right figure, we can see as the number of workers increases, the bandwidth overhead for dense algorithm is almost constant. This means that it has very good scalability. For top Ka, as the number of workers increases, the bandwidth overhead increases linearly. At some point, top Ka will surpass the overhead of dense Allreduce. And for top K DSA, it suffers from filling issue as the number of workers increase. And at some point, the all-gather phase will completely switch to dense format. For G-Topk, the bandwidth overhead is proportional to log P, although it's growing slowly, but eventually it will surpass the dense Allreduce. So overall, the existing sparse Allreduce algorithm suffer from a scalability issue. Therefore, we propose our own algorithm, Ok-Topk. It has less than 6K bandwidth overhead, which is more scalable than the other algorithms. Now let's look at the implementation details for OK Sparse Allreduce. So in the first step, all workers also select the local Topk values and their index. But here, we use an efficient local Topk selection algorithm based on threshold reusing strategy. We will discuss this later. And after that, the workers will partition the gradient space into regions, and each worker is responsible for reduction of one region. Here in this figure, we show that the gradient space is partitioned into equal-sized regions, but this may lead to scaled communication volume. As shown in this figure, the communication overhead on T3 is much higher than the other workers. Therefore, we partition the gradient space according to the number of Topk values, in which each subregion has approximately the same number of Topk values. And the partition boundary is re-evaluated after tens or hundreds of training iterations. Therefore, it can achieve balanced communication volume across the workers. After that, each worker will conduct reduction for the regions that it's responsible for. And the communication cost of the balanced sparse and reduce is modeled by this formula. And after the reduction phase, it will also conduct an all-gather phase. But before that, to get rid of the failing issue, we conduct another round of global Topk value selection. So here, in the figure, the checked block represents the global value and their indices. For global Topk selection, we also use an efficient threshold-based algorithm. We will introduce it later. And after that, each worker will package the global Topk values into consecutive buffer. You can see the global Topk value is also not uniformly distributed among the workers. If we conduct all-gather on these buffers, it will lead to severe communication workload imbalance. Therefore, before all-gather, we do data balancing using point-to-point communication. After that, we conduct a standard all-gather operation using recursive doubling. And then eventually, all workers will get the same global Topk values. So overall, the total communication cost for OK Sparse Allreduce is modeled by this formula. We can see the bandwidth overhead is less than 6K, which is asymptotically optimal and is also more scalable than the previous algorithms. Now let's look at how to efficiently select the local and the global Topk values in Ok-Topk. Here we use BERT pre-training on Wikipedia as an example. In this figure, the purple histogram shows the real distribution of the gradient values randomly selected from a training iteration. And the green histogram shows the Gaussian distribution, which has the same value of variance and mean as the real distribution. In the figure, the red line indicates the accurate threshold for Topk value. And the black line is the threshold predicted by the Gaussian distribution. We can see there is a big difference between these two thresholds. This means that the threshold predicted by Gaussian distribution is not accurate enough. Furthermore, we also observe that the accurate threshold is actually changing slowly as the training going on. Therefore, in Ok-Topk, for both local and global Topk selection, we evaluate the threshold once and reuse them in the following tau iterations. We call this the temporal locality for the statistics of the gradient value. Based on the threshold, Ok-Topk can only use On overhead to select the top Topk values, rather than On log n in the sorting-based Topk selection. Furthermore, the threshold-based algorithm is also more friendly to GPU than the sorting algorithm. Here, the blue line shows the threshold used by Ok-Topk. We can see it's very close to the accurate threshold. In the bottom figure, we compare the number of global topic values and the local topic values with the number of accurate topic values. In the zoomed subfigure, the yellow point represents the number of global topic values, and the blue point represents the number of local topic values, and the overlapped red point represents the number of accurate topic values. You can see they are very close. So this shows that the threshold reusing strategy is very effective. Now let's present the Ok-Topk parallel SGD algorithm. We can see it's very similar to the standard mini-batch SGD. But here we have three major differences. In line 4, we accumulate the residuals to a local buffer. The residue is the value which is not selected by Topk selection. And the OK Sparse Allreduce will return the indices of the values which really contribute to the Sparse Allreduce. In line 6, using the indices, it will remove the values which really contribute to Sparse Allreduce from the residue buffer. Next, let's analyze the convergence for Ok-Topk SGD. Here, we assume the difference between the true global Topk gradient and the Ok-Topk gradient is bounded by the norm of the dense gradient multiplied by a small constant C. So here we empirically prove this assumption using the real applications. After having this assumption, we can achieve the full proof for the convergence of Ok-Topk by referring to this Nurip's work. We also point out that the large value of C may have negative effect on the convergence rate of Ok-Topk. But the effect is also dampened by both small learning rate and the number of workers. So therefore, in the right-hand figure, the training for LSTM model, also the value of C is gradually increasing as the training going on. It doesn't affect the model accuracy. This is because the learning rate is also decreasing as the training going on. At last, we evaluate the performance on Piz Daint supercomputer. Each computer node of Piz Daint has one P100 GPU, and the computer nodes are connected by Carré arrays network. We use MPI4Pi as the communication library. And we compare the performance of Ok-Topk with the previously discussed dense and sparse Allreduce algorithm. We use 3 neural networks for evaluation: VGG, LSTM, and BERT. First, let's show the effect of communication balancing in Ok-Topk. Recall that in both reduction phase and altogether phase, we conduct communication balancing. So this result shows that the more number of GPUs we use, the more benefit we can get from the communication balancing. This is consistent with the communication cost model. Next, we present the weak scaling result for BERT pre-training. So these bars show the result on 32 GPUs, in which the dark blue block represents the computation cost, and the blue block represents the communication cost. We can see Ok-Topk achieves the lowest communication cost. Furthermore, we show the result on 256 GPUs. We can see as the number of GPUs increase to 256, the communication overhead for Topk A and Gaussian K increases significantly. This is because these two algorithms all use altogether-based Sparse Allreduce, in which the bandwidth overhead is proportional to the number of GPUs used. And for Topk DSA, because it suffers from failing issue, the communication overhead also increased significantly. Next, for the light blue block represents the overhead for Topk selection. For Topk A, Topk DSA, and G-Topk, they all use the sorting-based Topk selection algorithm. We can see they have very high overhead for Topk selection. Alternatively, for Gaussian K and Ok-Topk, they both use threshold-based Topk selection algorithm, which has very low overhead for Topk selection. Overall, we show that the Ok-Topk has much better parallel scalability for communication overhead than the other algorithms. And it also shows that the threshold reusing strategy is very effective for Ok-Topk. These figures show the model accuracy result for 3 neural networks. For all these 3 deep learning tasks, Ok-Topk achieves the fastest time to solution. At last, I conclude this work. First, we show that the model size is growing exponentially. And to reduce the communication overhead, people propose to use Topk SGD. However, the Sparse Allreduce algorithm is not scalable. Therefore, we propose our own algorithm, OK Sparse Allreduce. It incurs less than 6K communication overhead, which is more scalable than the other algorithms. Next, we present Ok-Topk SGD and analyze its convergence. And at last, we evaluate the performance on Piz Daint supercomputer, and the results show that Ok-Topk achieves the fastest time to solution. For the future work, we will study how to use Ok-Topk with a hybrid data and pipeline parallelism. That's all for my presentation. I'm happy to answer any questions.